Okay, let's continue our discussion on enzymes, and let's focus in on what we call enzyme catalyzed reactions, kind of give you an overview of that. And then let's look at two models, how enzymes are often referred to as using a lock and key model or an induced fit model. Kind of a few more details or descriptions on how they work, their methodology, so to say, in biological reactions. Okay, so enzyme catalyzed reactions, okay, this is where we take an enzyme plus a substrate, they come together within the active site, and they form what's called an enzyme substrate complex, okay, or an ES complex. Okay, so the enzyme and a substrate within that active site come together, okay, makes an enzyme substrate complex. Okay, now within that active site, okay, so we focus then on the R groups. So R groups within active site. Okay, these R groups within the active site catalyze the reaction. Okay, they catalyze the reaction. Okay, and then what that leads to, okay, leads to what we call an enzyme product complex, or an EP, an EP complex. Now, these R groups, I failed to mention, these R groups that are within the active site that catalyze this reaction, okay, that gets the process to work. Now, those R groups are the R groups on the amino acids that are found within that active site. So the amino acids are there locked together with the peptide bonds. Those amino acids together, you know, are the active site. The amino acids have specific R groups. Those R groups will catalyze the reaction, okay, creating that enzyme product complex. Then what happens? The product is released. Okay, then the product is released. Okay, moves out of the active site, goes away. The active site is still active. It's still available. The R groups within those amino acids are still available, and so another substrate can move in, lock into place, repeat the ES complex, repeat the catalyzing of the reaction to make the EP complex, and then the release of the product. Okay, so it can continue over and over and over, cyclic, like an assembly line, continuous, repetitive process. Okay, now let's dive into a little bit of detail on what's called the lock and key model and the induced fit. Okay, so the lock and key model was the idea that the active site, okay, the active site, being a very rigid, non-flexible shape structure, very solid, very rigid kind of structure, okay, and then the shape of the active site was the comparison of being the lock, okay. Its substrate, okay, so then the substrate was the key in the lock and key model, and the key could fit that lock specifically, okay, so much like a doorknob, the doorknob is locked, and there is a specific key that's got a specific shape, specific size that can slide into the keyhole and unlock the door, unlock the lock. Okay, so the lock and key model was the idea of the active site being very rigid, non-flexible, specific shape, size, however you want to describe it, okay? And the substrate, okay, would be the key, okay, would be the key that specifically fits the lock, slides in, unlocks the door, so to say. Okay, this model isn't completely accurate because we have to remember that the tertiary structure of proteins, okay, so we're talking about the enzyme, the tertiary structure of the enzymes are flexible. They're flexible, so to say, elastic. And so they can bend, they can move, they can fold, they can twist. So the active site then has an ability to slightly adjust or morph its shape, its size, so that the substrate can fit in. Okay, it's what's the word I'm looking for? Moldable. Okay, it's moldable. Okay, so that's one downfall or one shortcoming of the lock and key model. Now the induced fit model is a more dynamic model. Whereas lock and key is considered static, stationary, set. Dynamic is more flexible, adaptable model. Okay, and it says that the active site is more flexible and allows for morphing, transformation, changing the shape, the size of the substrate, so to say. At the same time, the shape of the substrate can be modified, okay, to better fit the active site. So that here in the induced fit, we can look at it as being the active site and substrate are more flexible, adaptable, okay, adaptable. To induce the fit, to create the right shape, the right size. Okay, they can kind of flex, they can move around. Okay, or you can even think of it as changing the geometry, the geometrical shape. Okay, the adjusted fit of the active site provides better alignment. Okay, better alignment for the catalyzed reaction to happen. Because remember, one of the key points of the collision theory is not only that the reacting molecules need to collide with a threshold amount of energy we call the activation energy, but they must also collide with correct alignment or orientation. Okay, so the induced fit model allows for that. Okay, that both the substrate and the enzyme can work together. Okay, they can work in partnership or cooperatively to create the right geometrical shape, structure, arrangement that will lower that activation energy of the reaction.